So if a 10-foot ladder leans against the wall and the bottom slides away at 2 feet per second, as we have written here, how fast is the top going to be sliding down the ladder when the bottom is 6 feet from the wall? So our first step here is going to be to identify our equation, which is going to be x squared plus y squared is going to be equal to 10 squared, which 10 being the length of the ladder. And then from here, we're going to differentiate or find the derivative with respect to time. So that's going to be 2x dx over dt plus 2y dy over dt is going to be equal to 0, since the derivative of 10 squared or 100 is 0. And then at x is equal to 6, y is going to be equal to 8. And then from here we can plug in our values. So we can go 2 times 6 times 2 plus 2 times 8 dy over dt is going to be equal to 0. And then if we simplify this out, we go 24 plus 16 dy over dt is going to be equal to 0. And then dy over dt, when we isolate, is going to be equal to negative 1.5 feet per second. And it's negative because it's obviously moving down. So it's when the base of the ladder is 6 feet away from the wall, the top of the ladder will be moving negative 1.5 feet per second down the wall. Let's try the next problem. So a spherical balloon is being inflated at 100 centimeters cubed per second. Find the rate at which the radius is increasing when the radius is equal to 5 centimeters. So once again, our first step here is to find our equation, which is going to be the volume equation. So volume is going to be equal to 4 over 3 pi r cubed. And then from here, we're going to differentiate, again, with respect to t. So dv over dt is going to be equal to 4 pi r squared dr over dt. And then our next step here is going to be to plug in 100, since that is the given information we have in our question. So we're going to go 100 is going to be equal to 4 pi 25 dr over dt. And then when we simplify this out, 100 is equal to pi r dr over dt. And when we isolate for dr over dt, dr over dt is simply going to be equal to 1 over pi centimeters per second. Let's try one last problem together. So water is poured into a cone with a radius of 5 meters and a height of 10 meters at a rate of 3 meters cubed per minute. How fast is the water level rising when the depth is 6 meters? So first, we need to once again use our equation, which in this situation is going to be the volume equation. So volume here is going to be 1 over 3 pi r squared times height. So this is going to be the volume for a cone. And then we need to use a ratio. So our ratio for R to H is going to be equal to 5 to 10, which you can also write as 1 over 2, or you can write it as h over 2. So essentially the radius is equal to h over 2. And then we can substitute in. So now v is going to be equal to 1 over 3 pi, and then the radius squared, which we said is h over 2. So h over 2 squared times height, which when simplified is going to be pi over 12 times h cubed. And then next we can differentiate, or we can find the derivative. So dv over dt is going to be equal to pi over 4 h squared dh over dt. And then lastly, we can plug in 3, which is our rate. So we'll get pi over 4 times 36 times dh over dt. And then what we'll be left with, essentially 3 is equal to 9 pi dh over dt. And when we isolate for dh over dt, we are going to be left with it equal to 1 over 3 pi meters per minute. So essentially for related rates, we need to remember to write an equation, differentiate with respect to time, and then plug in our values. And with practice, you'll see that most related rates problems really follow the same pattern. I hope this video helped. Thank you.